Thank you all for coming today. This is Erla, and we are going to get a fantastic presentation. Put it together for Erla.
Thank you. Am I live? Okay. So I'm going to talk about build system failure modes. I can't see most of you, but if there's a build system, you might have used it as a developer, especially in an iterative way, that you change some stuff and then you rebuild. And this is all about what can go wrong and how you shouldn't do it and how you might be able to fix this. So first question is what's the topic of the talk? What is a build system? In its most basic way, a build system evaluates rules and consumes inputs, generates outputs, and you can, if you only change some of the inputs, partially evaluate the build and not recompute everything, but only the things that should be recomputed. Which necessarily leads us to, okay, Make is a build system, CMake is a build system, Ninja is a build system, but Excel, in that sense, is also a build system. Yeah, you have formulas and inputs, and no one prevents you from, I don't know, making a roguelike in Excel. But it's actually relevant to the formalisms that you would use to analyze this. You want your outputs to change when you change the inputs, but you do not want to recalculate entire spreadsheets when you press one key. So the thing is, build times matter. Someone suggested I should include this compiling comic from XKCD, but she also said, if you had one dirty sock, would you wash all your socks again? And same is if you have one dirty file, how would you get a clean build? How would you like it? If it didn't take 40 minutes, but 4 minutes, the only way you get there is partially rebuilding only what you need to change. Many people think build times don't matter. That's usually because they have beefy computers or, I don't know, pipelines or whatever. Your reality might change. It might be that stuff takes hours. I personally got into build systems because I had a podcast, static site generator, and if you mess anything up, then there are lots of audio files which want to be re-encoded, so I had no really motivation to get this wrong. If I accidentally do stuff that I shouldn't, it would have taken hours. And if I had always rebuilt everything, I wouldn't be done at any point. So now the thing is, you want to rebuild target files when their prerequisites change, and I will talk. This talk is structure 3 parts. First, common issues. You might have noticed these, but only have a feeling or ignored them or something. Many people do notice them, but think, yeah, it just happens. Then why do these happen? Why I think they do happen? Maybe you have different opinions, but I think I'm right, because obviously. And then an example of how to do that correctly, which is not as seen as an advertisement, but more if you change how you approach the problem, then you can actually do a lot of tasks in a much simpler way. Yeah. So first, common issues. So your target files do depend on source files, and you can simplify this. Well, if you build some other target files, they can also become source files for some next step. And there are 3 popular approaches. Well, the first one is very popular, the last modified timestamp. When did I touch this last? And if you touched it, then the target is out of date and something needs to be rebuilt. There's a file, you edited it. The thing doesn't even check if you changed anything. You just you open it, saved it, and the timestamp in the file system gets updated. The build system figures out, oh no, the source file has changed. Now I need to compile again, or I don't know what, or convert some media files. More correct approach, so to say, that lets you rebuild less, is hashing everything. But the problem is that hashing, again, takes time. So a really good approach is check the last modified timestamp, and if it's mismatching, only then hash. Depending on what approach you use, you might have problems. For example, with the first approach, you have the problem that Git touches everything it sees when you do a checkout, so stuff gets rebuilt all the time, uselessly, if you use make. But with the hash thing, I once generated a 16 GB sparse image for some SD card. Yeah, and then the build system hashed it, and it took a long time. That was not very smart of me. But basically, you know this issue. The second thing, well, it's the same. I'm sorry, I should have gone there. Yeah, the first is wrong, the second is slow, and the third is fast and correct. So there's no excuse for build systems that use the last modified timestamp to like not hash to avoid users' busy work. So then the second thing is dependencies are actually recursive. Like people only often think, oh, I checked the file, it's up to date, and that's okay. Yeah, it's now I can just forget about it. But you not only have to like check the thing, your dependency, you have to check all the dependencies of all your dependencies. Like if you generate some source code file from something else and then you compile something from that, one thing taints the entire chain. And if any prerequisites of anything, regardless how far away it is, changes, the target needs to be rebuilt. Some build systems forget this, to which I'll be coming. So one thing that often happens is that people underspecify their dependencies. Yeah, you have to list all of them, and maybe you have to list them manually. And the timestamp-based build systems rebuild often anyway because you use Git, or maybe you finger all the files and have them all open in your editor and it autosaves. So the problem is that the second thing that the timestamp-based build systems rebuild so often that masks it. Like you will maybe never, as a developer, get a failing build. Because like, yeah, it rebuilds lots of useless stuff anyway without needing to, and that prevents you from noticing it. The prime suspect is Git checkout, and it's really hard to convince people of that this is happening, but what you can do is make a post checkout hook for Git that sets the timestamp of the files that you checked out to when they were last committed, and lots of things will break. I can guarantee it because I tried it, and then people were like, yeah, just don't do that, but it's more like proving that the dependencies are underspecified. Pretty easy experiment. So one thing that is often ignored is that target files actually depend on their own build rules. So if the build rules change, the target needs to be rebuilt. That sounds obvious, right? I have a different build rule, and my favorite build system, Excel, does this right. If you change the formula, the cell is updated. But Make does not, and neither do a lot of other systems that basically work like Make. The trick question is, should targets depend on the Make file? I have rarely seen this in the wild. The advantage is, whenever you change your build rule, your target is rebuilt. The disadvantage is, whenever you change any build rule, all targets are rebuilt. Yeah, to me it suggests that maybe the idea of like putting all the rules in one file and so on is done, but it's a funny trick question. Like maybe if you meet someone who didn't go to this talk and they're like really enthusiastic about build systems, that could make them shut up. So then something that is ignored even more often is that targets actually depend on non-existent files. It might be that a new file appears and the target needs to be rebuilt. A header file appears in the current directory and your preprocessor would find it. Or you have an image gallery, a new image appears. You do not want to rebuild all the thumbnails, but the index file that shows all the pictures needs to be invalidated when a new image appears. And if you have a webcam that does a photo every minute or so, you already know the file name of the non-existent file that as soon as it appears, invalidates your build. A surprisingly large number of build systems are entirely unable by architecture, like architectural limits, to actually do this and ignore it entirely. But the problem is this is a very common thing, and basically every one of these non-existence dependencies is the case of I make a new file in the file system and this invalidates my build. And if I then rebuild, I might get a binary that doesn't correspond to my source code. That all of the problems where you have a build that seemingly succeeds, like not goes on, but doesn't build enough, mean your result is not guaranteed to be correct. Maybe some of you had this, that they partially rebuilt something, it didn't work, and you deleted like all the make and CMake files and whatever, and then you rebuilt completely, and then it worked. Yeah, that was one, maybe not this one, but this is one of the common issues. Often people don't know why it happened, but you can blame the build systems, basically, for not tracking something that it should have tracked. So now the thing is, even more specifically, combination, targets depend on non-existent build rules. It might be that in the future, a target that is built using a general rule, like a rule for all HTML files or all object files or something, in the future you have a more specific rule that would override this. Yeah, well, when this rule appears in the make file, which we already know is rarely considered anyway, you also need to rebuild the target. I've actually never seen this in software that's like unrelated to the proposed solution. Like it seems to be often forgotten, or people use weird domain-specific languages to handle this. Yeah. So the thing is, like, why do these problems happen? And I am convinced that the reason is because the common approach to build systems is you treat everything as a directed acyclic graph. That's an image from Wikipedia, where the nodes are files, like in the graph, and the edges are dependencies. Like to build A, I need to build C and B and C both need D, and D need E. So I first start. I have this information, and then the procedure is I construct this graph, I topologically sort it, so I have an ordering in which I can build these things so that they satisfy all these arrows there, and then I schedule the build task. And this is very easy to implement. It's very easy to parallelize, and it's obvious but wrong. Because while your idealized build, the spherical cow in a vacuum, might sometimes be modeled like that, usually you don't want that. Because at the point where you construct the graph, you do not have enough info. Like, you cannot actually do this successfully in almost all cases that I can say. For example, because you do not know the non-existence dependencies. Like, you do not know which file the preprocessor did not find and did not include, but would find in the future. And as soon as you have scheduled the build task, you might get new information. Like, the thing is, like, to deal with this, people pretend, for example, that the world is frozen, that the entire file system is the same as when you started the build. But the problem is, obviously it isn't, because you're outputting stuff and generating files left and right, because that's the purpose of your system. So it's kind of a bit weird that people then, for the dependency evaluation, pretend, well, all this still like it's in the start, it doesn't work. The second thing is, like, there are some people who are like, oh, just list every dependency. Yeah, you're a programmer, list every file. Yeah, this obviously does work, and embedded developers rarely have these kind of problems because they seem to be like a special breed and have very little in terms of dependencies. They know absolutely nothing, but compared to application developers. But if you have a build system that says, oh, if you don't list the dependency, it will not show up in the file system view for the build, because of some overlay or so, then you will be annoyed pretty fast, because it's fucking robot work to like figure out which files are there. Like, why should you do that if the computer can do it for you? So the most popular approach to make it work is just ignore the issues, like the previously mentioned problems and similar problems that result from this, because it's oh so seducing to have a way that you can easily model something, and maybe it's sometimes wrong, but it's fast, right? And you totally understand it. Build system authors do not like it when you point out that they're ignoring stuff. I've literally seen people say, well, then just don't do that. Like, don't have that build, but that doesn't help me because I have the build and I want results. So how would you do it correctly? What I figured is that actually, you can treat builds as some kind of like huge function that you can partially evaluate to partially rebuild, and then you can rebuild recursively until the outputs change, like until you reach a fixed point. Obviously, the one iteration is a common case. You get something, you get the output. If you would do it again, you get the same thing. But if you use this make depends thing, where you use make and it outputs, and the compiler outputs the dependencies in a format that make understands, and then you rebuild a second time, and then you get the same output. You have 2 iterations, and you have found your fixed point. And perhaps the most common example that people are familiar with is LaTeX. Like, you have these like line numbers and references and figure stuff, and you need to compile 3 times because the build needs to be iterated until you reach the fixed point where everything points to the correct page. This is kind of obvious once you see it everywhere, that intuitively you expect the thing to have a fixed point. If it not, you have a halting problem. But obviously, you cannot model the LaTeX thing with a directed acyclic graph. So Daniel J. Bernstein, long time ago, put some notes on the website and never released the tool. I met him twice and he didn't. So how to fix a bunch of stuff. I read them at some point when I did the podcast thing. And someone else wrote a thesis on the topic, like how build systems should work. And several implementations of this idea were created, mostly incomplete. I also have one, I consider it complete. The important thing is, like, because Bernstein never released it, I don't know if he has one, but he writes makefiles the way someone would translate them from another tool sometimes, or maybe he does it in his head. So, like the same way you can like spot the Python code that was written by the C programmer who is barely familiar with Python. So the essentials is basically the idea allows any language to use to create some targets, like just no special thing, like use shell scripts, use Python scripts, use Ruby, whatever, random executables. But you have to build top down instead of bottom up, which means when you start the build, you do not start at the leaf nodes, at the stuff that you need to like build higher stuff, but you start at the end target. Like, I want this binary. What do I need to do to get it? Then you recurse down to the sub-targets more and more. This is, for some reason, people don't like this approach, but you avoid the topological sorting and a bunch of other issues like that. And also, build rules are files. This will become important later. Because each build rule is one file, this means you can change the build rules the same way you track change to files. You do not need a different first-class primitive that you can depend on. And if a build rule changes, all its targets are rebuilt. And obviously, if you have more specific build rules, they will have different file names, and you can have a more non-existence dependency on this not yet existing, more specific build rule. And if that file is ever created and you write a build rule in it, the target will be rebuilt. Solves a bunch of issues. People hate it because then they suddenly have more files. There are 4 commands which make this possible. I have a separate talk that I can give you, like not here, but that explains how to use them. But basically, these are primitives. If you implement these 4 primitives in your top-down recursive build systems, I think you can avoid most of these problems and have something that is very small in terms of implementations, very flexible because you can combine them in weird ways, and actually is correct. And faster than the tuposort thing for many common cases. So the first command is a redo if change. Basically, you have some script that builds something, maybe a shell script or something, and redo if change is a command that only has a meaning within a build script for a target. And it means first, it checks if the file is out of date. Like, it can be something that you generated, or it can be a source file. Then it rebuilds it if necessary. Obviously, it will only happen for stuff that you generate. And third, if that thing was out of date at the point where this command was executed, like the argument to this command, a file name, then the current target is rebuilt. This is a bit weird, but it's a really powerful primitive that enables you to make, basically this means, oh yeah, this thing is a dependency, but it enables you to declare this in an imperative way, from within a shell script or from within a Python or C program. As I said, it's a bit weird. The second, redo if create, basically the same thing for the non-existence dependency. First, you check that the file argument does not exist. Second, if that thing exists in the future, the current target will be rebuilt. Don't think too hard about how this is implemented. It's a bit brain teaser. Then people often forgot this, but Maker's phony rules and other systems have as well. There's a command that you need to mark a target as always out of date. And here you see the directed acyclic graph thing will have a problem with that. Because if you have something that's always out of date, and then you do the topo sort, it only appears once in the list. But it may need to appear several times, because it's always out of date when you want it. So you always need to rebuild it whenever anything depends on it. So you can actually spot build systems that do not handle a case correctly by figuring out how they make targets always out of date, and then figuring out if you have like several things depending on an always out of date target. Is it built only one time? If yes, the build system is faulty in a way that makes it way easier to implement parallel builds, but also makes them incorrect. So there's one fourth thing that you need for some reasons, because sometimes you might notice during a build that something that you built, while it was considered out of date, is actually up to date. For example, if you have a target that depends on something that is always out of date, you might want that always out of date thing to be regenerated. But the thing that depends on it, by the transitive property, would also be always out of date, and then you would end up rebuilding everything all the time that depends on anything that at some distant point in the graph is out of date. So basically this tool reads the standard input, and if in any future build the input is the same, then the build is only speculatively executed up until this point, and it says, oh no, the target is up to date. Everything is okay. And this is very rarely needed, but when you need this and your build system cannot provide it, like actually canceling a scheduled build command during a build to save time, because it would be useless busy work, you will totally notice it missing. So this is the end of the explanation, and I have a few more slides. I hope, can I still continue? Okay, then come to me afterwards, and they are very predictable questions. I can answer most of them, and if you want to fix a build system or whatever, talk to me.
Let's have a great round of applause for Ella.
Yeah.